Hello, everybody. I hope your week is going well. I'm here to talk a little bit more about thermodynamics, and I hope everything is healthy and happy with you. We're going to get into more in the second law today, but first, I wanted to make a couple of announcements and talk a little bit about what we did last time. So, first is that I want to make sure that this lecture format is working for everybody. I know that I have, been going on doing these pre-recorded lectures for some time now, and there's been some discussion in the department and really all over the world and country about what's the best way to deliver this online content to you guys. I've decided to do what they call as asynchronous or sort of pre-recorded lectures that you can view at any time, as opposed to a synchronous lecture, which means that all of us would be gathering Monday, Wednesday, Friday at 8 a.m. I really would value your feedback, so if you could send me some email if you have any thoughts on the subject. If it's working for you, great. You don't need to send anything to me. I mean, but if you really feel like you prefer a little more of a synchronous lecture structure. If that's important to you, please let me know. If there is any suggestions on how to change the format of what we're doing, that would also be great. I also probably will put out some sort of survey that you can take and maybe so if you give me some feedback on how things are going, because now we're kind of through a couple weeks or more of this thing, and I feel like I'm getting into a groove, but maybe that is not the way you feel. So, um, great. Other things, yeah. So we have the survey from last week, or last week or from Monday, and I'm going to go through that now and see how everybody did. So remember we were talking on Monday about irreversibilities, essentially non-ideal processes that you can't take back. That's really what it's all about, right? And that's what an irreversibility is. Now, if we look at the question here, it says, which of the following is not an irreversibility? The answers came back from all different, everybody had one of the answers, so that's good. So we have heat transfer through a finite temperature difference. So remember, we did a couple of example problems in the class on Monday where we looked at these different examples. One was the two bodies in thermal communication with each other, exchanging heat. And we said that was an irreversible process. So that definitely is an irreversibility. You can't take it back, right? So the idea is, well, once you transfer heat from a hot body to a cold body, you can't take it back again without doing something to make it happen. Spontaneous expansion, same deal, right? We did an example with a valve in a tank, the Joule experiment, where we go through the valve and you can't put the stuff back, right? And I was having breakfast a couple days ago, and my kids were asking me about what I'm teaching about, and I said I'm teaching about the second law and about irreversibilities. And the example came up of to explain it, about the coffee. So you have the coffee with some milk, and you pour the milk. I take my coffee black, but my wife drinks it with milk. She pours the milk into the coffee, and you can't take that milk back out. Mixing, you can't unmix the cream, right? So it can say, "Oh no, I put cream in your coffee. I'll take it back out again." You can't do that, right? That's entropy. That's the second law. Likewise, when you bend something, like this, the answer here, elastic deformation of a material. Like if you bend it and it comes back, that can be considered a reversible process, possibly. Not always, right? There's no really such thing as a perfectly reversible process in practice, though idealized there is. But an irreversibility would be some sort of elastic deformation. So inelastic deformation. So inelastic means it yields, like the bar like bends. I took my pencil and bend it, and so it doesn't come back. Friction is the classic example of an irreversibility. So friction is, here this, the friction is sort of an example where, we always say, what's an irreversibility? Friction is always given. It gives off heat. You can't take it back. So think about an irreversibility as something that it's a loss. It's something you can't take back. Something that's not possible to make up for. Okay. So so that's the survey. I had 57 responses, so not everybody participated in the survey. I hope that you will continue to participate in the surveys because it gives you some motivation to watch my lecture. I'm hoping that you have more motivation to watch it, and we can keep this process going the way it's been going, because I think things are going pretty well. Let's talk a little bit about the new stuff then. All right. So last time I talked about idealized process for a power cycle operating between two thermal reservoirs, and we use this power cycle idea to prove that a couple of different situations, like this one with the valve and this one with the heat transfer, were irreversible. Okay, and so we use that concept. Here we're going to talk about the same kind of thing except with refrigeration cycles. So we're going to have a refrigeration cycle operating between two reservoirs, and while communicating thermally to reservoirs on a hot reservoir and a cold reservoir. So we already know from our previous discussions that the coefficient of performance for the refrigeration cycle is given as this equation. So beta equals QC over the work that you put in. QC is the work that you desire, or the heat that you desire to cool a space or refrigerator. Okay, and for the heat pump, the cycle is the QH, because always efficiency metrics are what you want over what you put in. In this case, QH over work cycle, QH is what you want. You know, for that, when I talked about how people in warmer climates heat their houses, they use a heat pump, which is the opposite of the refrigeration, their air conditioner. So yeah, that's generally how we say it. So we want the QH, so that's what you want in the case of a heat pump. So that we call it gamma. All right. So those are the coefficients of performance. We know this already. Now the question is, what's the ideal coefficient of performance for a refrigeration cycle and for a heat pump? That's what we want to know. Okay, so by applying the Kelvin-Planck statement of the second law, we can draw three conclusions, and we did the same three conclusions for the power cycle. We can draw the same three conclusions for the refrigeration and heat pump cycles. Okay, for a refrigeration cycle, or for refrigeration to occur, we know that we need to put work in. That's the Clausius statement of the second law, right? You can't exchange heat you can't send heat from a hot body to a cold body without putting work in. Okay. Accordingly, the coefficient of performance must be finite in value, meaning that you can't have infinite coefficient of performance. Think about it, right? If work cycle goes to 0, these terms go to infinity, right? So you have to have a finite, COP or beta or gamma. Okay. Two other conclusions that we can make are the coefficient of performance of refrigeration cycle is always less than the coefficient of performance of a reversible one. This says actual, sorry. Of an actual irreversible refrigeration cycle is always less than the coefficient of performance of the reversible one. So just like we said for the thermal efficiency, the actual efficiency is always lower than the ideal thermal efficiency of a power cycle. All reversible refrigeration cycles operating between the two same thermal reservoirs have the same coefficient of performance. That's the same thing we said for a power cycle. So if we go back up to my slides here, so you just go back up to the slides I presented for Monday's class. It looks like the same thing, right? So this one is the value of the thermal efficiency must be less than 100%. Thermal efficiency of a reversible power cycle is always less than the thermal efficiency of a reversible one. All reversible power cycles operating between the same thermal reservoirs have the same thermal efficiency. Okay, so that's all pretty much the same as what we talked about. And so essentially what we're saying is that you can never get as good as the reversible cycle, right? That's all we're saying here. So the reversible cycle is noted as the ideal. Okay, so we're going to do an example on this a little bit later, but I think this kind of gives you the idea of what we mean with regards to heat pumps. It's just pretty much the same thing, right? So now we have the efficiency definitions for power cycle, heat pump, and refrigeration cycle. Now we want to consider the Kelvin temperature scale. We talked a little bit about the degrees Kelvin, right? So there's an absolute zero, and there's some law called the zeroth law that defines absolute zero of the thermal equilibrium and absolute zero. But let's consider systems undergoing a power cycle and a refrigeration or heat pump cycle while exchanging energy with hot and cold reservoirs. So here's on the left is the classic power cycle. We have work cycle as the net output positive, Here we have work cycles in at negative. You have heat going from the cold reservoir to the hot reservoir. So these are the two different classic examples of the cycles, right? The Kelvin temperature scale is defined such that the ratio of QC to QH for a reversible cycle equals TC over TH. Okay, so this is kind of important. What this means is essentially that we can say that the temperature ratio in the heat ratio is the same. So just by definition, okay, so we define the temperature scale to be that way. And so that's where we get the temperature scale that it is, right? So the idea that you have an absolute zero. So when you have TC is absolute zero, then your ratio is zero, right? So the Kelvin temperature scale is defined this way. Here, let's make sure I'm fixed in place here. And then, so in words, when the reversible, get myself situated here. When cycles are reversible, then and only then is the ratio between heat transfers equal to the temperature, Kelvin temperature, where TH is the temperature of the hot reservoir and TC is the temperature of the cold reservoir. Okay? As temperatures in the Rankine scale, yeah, so Rankine and Kelvin are different, right? So this is just a caveat for Rankine. By a factor 1.8, the temperatures in the equation, 5.7, this is from the textbook. Temperatures 5.7 is this one. Is valid for temperatures in degrees C or degree Fahrenheit. They don't vary from Kelvin temperatures only by a factor. However, you cannot use Celsius and, let me get this. Let me get rid of this here. We can't use Celsius for this ratio, right? So because that Celsius and Fahrenheit are not absolute temperature scales. They don't go to zero at zero, right? So it's important that we have we use these absolute temperature scales in order to define this efficiency metric. Okay, so previous deductions of the Kelvin-Planck statement of the second law include thermal efficiency of a reversible power cycle is always less than the thermal efficiency of the reversible power cycle when each operates under the two same thermal reservoirs. So we know that that's true. Likewise, we know the same exact thing is true for the refrigeration cycle and for the coefficient performance of a heat pump. Okay, so we know that both of those things are true. So when they operate between the same two thermal reservoirs. Okay, so we know that no matter what, if it's a reversible cycle and it's a heat pump or power cycle, no matter what's in there, what is a gas turbine or engine or whatever it is, has the same ratio, right? Why do I keep on losing myself here every time? Okay, here we go. So the maximum performance for cycles, if we think about what the maximum performance is, for a power cycle, the maximum efficiency is 1 minus TC over TH, because it's 1 minus QC over QH, right? So we just replace the QC over QH, and we get 1 minus TC over TH. Likewise, for beta max, we get TC over TH minus TC, and gamma max equals TH over TH minus TC, where those must be on a Kelvin or Rankine scale. Okay, so we have new relations now, essentially, where we can say that the maximum thermal efficiency that you can get from any power cycle or any cycle is in proportion to the temperature of the thermal reservoirs. This is really important, so you're going to need to know this. We're going to do some examples. This is only true if you use the Kelvin or Rankine scale, okay? Those are absolute temperature scales. And this is for idealized cycles. You can't just say any cycle has this efficiency. This is for the idealized maximum efficiency of any cycle operating between these two reservoirs, okay? So, all right. Somehow this is not locking in the right place, and it's annoying me. Okay, so what we're going to do is, now that we have this ammunition here, we're going to need this ammunition right here. We're going to do a couple examples that kind of go through this idea. And we'll talk a little bit about it before we get into what we know as the Carnot efficiency, which is the Carnot efficiency is defined like this. Okay, so let's first do a couple examples, and go from there. All right. And then you'll get a chance, of course, to practice them. You'll get a chance to practice them at home and, for your homework for Friday. Okay, here we go. Here it is. Maybe it's best to actually look at this on my iPad here. So look at it on my iPad. All right, two reversible refrigeration cycles are arranged in series. The first cycle receives energy by heat transfer from a cold reservoir at Tc, and the second rejects energy by heat transfer to the reservoir at an intermediate temperature T greater than Tc. And the second cycle receives energy, blah, 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 from T and goes into Th, right? Obtain an expression for the coefficient performance of a single reversible refrigeration cycle operating between the cold and hot reservoirs Th and Tc. Okay, in terms of the coefficients of performance of the individual cycles. All right, so let's do this. So what we have two refrigeration cycles in series between a common reservoir at temperature T. Okay, what we have to find is the beta of the whole thing as a function of beta 1 and beta 2. Okay, so that's our goal, is to find the two things. If we have two refrigeration cycles, we have two systems. So let's the next thing we do is make an assumption. So let's make assumptions. The first one we're going to make is that these are steady state cycles. Two, we're going to assume that they're reversible cycles. Okay, so those are our assumptions. I don't think we have to make any other assumptions here. No, I don't think so. So let's make our diagram. I'm going to make our diagram, I guess, over here. It's a pretty short solution, so hopefully we can just get it done in side by side here. I'll put our analysis over here. Okay. Yeah. All right. So the diagram looks like this. So you have one thermal reservoir here at TH. You have some heat transfer going. Oops, it's going the other direction. Forgot. Oops. Let's see. We have a cycle here, and we have some other thermal reservoir here at T. And then you have another cycle. I don't like my circle here. Gotta make a better circle. Okay, and then not really that much better. So TC. All right. Okay, so here we go. We have these two cycles. They both have some work. So we'll call this I don't know which one is one. It doesn't matter which one is one and which one's two. We're going to call this cycle, we'll call this their system 1. And we got another one here. We got system 2. Okay, we have, so then this is work 1 and this is work 2. Okay, so those are our two things. Let's see, now what do we need to know? Well, I guess since we know that the ratios of these, we know the ratios of what these coefficients of performance are based on the temperatures. But I think we'll just say that in general we have some, we'll call this QC, and we'll call this QH. Okay. All right. So then let's do some analysis here. So the way we're going to do this is that we're going to use the equations that we derived, right? So the equations we derived are right here, right? So that we've got beta, right? So I'm just going to write this down. So beta 1 is equal to Tc, well, no, beta 1 is going to be equal to Th minus T. Okay, like that. Okay, and then, so beta 1 equals T over Th minus T, right? And likewise, beta 2 is going to be the same thing, is equal to Tc over T minus Tc, right? Okay, so let's see. Let's solve this one for Th, because the thing we don't know is what the overall coefficient of performance is. Oh, well, I'll just write that down. So the overall coefficient of performance is equal to Tc over Th minus Tc. Tc, right? And that then essentially what we're going to do is we're going to solve each of these equations for the temperatures, right? Because we're going to assume that we know, because in the problem we're assuming that we know what the beta 1 and beta 2 are. So we're going to solve the temperature ratios as a function of the temperatures. So Th over T is equal to 1 plus 1 over beta 1. Okay, if we kind of manipulate this, so multiply both sides by Th minus T, and then you could divide by T, and then that's what you're going to end up getting, right? And then so we'll do the same thing as get this ratio. So we're going to have T over Tc equals 1 plus 1 over beta 2, and then we're also going to get Th over Tc is equal to 1 plus 1 over beta. Okay, then essentially we know that, then we also know that Th over Tc, right, is equal to Th over T times T over Tc, just because, obviously, right, if you just multiply both top and bottom by T, you get this relation, right? And so example 1 continued. Okay, and then so essentially what we've got now is we have to combine all these things together. So let's see. Let's go here. So let's 1 plus beta equals Th over Tc. So let's go like this. We have 1 plus 1 over beta. Let's see, we're going to do it this way? Yeah, okay. 1 plus 1 over beta is equal to Th over Tc, which is equal to Th over T. Here, Th over T times T over Tc, which is then equal to 1 plus 1 over beta 1 over 1 plus 1 over beta 2. Sneaky, right? Tricky. Okay, so then essentially we're going to rearrange this guy, and we're going to end up getting, so we have a pretty good thing here. So we just want to solve this thing for beta, right? So then we're going to get up like 1 over beta, so we can add 1 to that side. 1 over beta is equal to beta 1 plus 1, beta 2 plus 1 over beta 1, beta 2, plus, minus 1. And then essentially we can just solve it then for beta, and we end up getting beta is equal to beta 1, beta 2 over, let's see, beta, oops, that was wrong. Beta 1 plus beta 2 plus 1 on the denominator. So it's just a bit of messing around with the algebra, okay? And so this is the final solution for the overall beta as a function of the other two. Okay, so that's for this system where you have two things in series. So you'll have a chance to practice some more stuff like this, just manipulating these equations and kind of trying to figure that out. The key trick to this one was this part right here where we had this ratio, um, and we use that relation. Essentially, it's just a mathematical trickery. Okay, so just keep that in mind. Okay. Now the second example that we're going to do. Let's see if I can get to the second example. Okay, oh yeah, so we're going to talk a little bit about power cycle next. And this is an example that I can just do on the slides, so I don't have to write this one out, but you can see it's on the slides. This one kind of comes with the slides, so that's good. Okay, so a system undergoes a power cycle by receiving 1,000 kilojoules of heat. So now we're talking about power cycles from a thermal reservoir at a temperature of 500 K and discharging 600 kilojoules. So we know the Q's. Okay, 1 minus QC over QH is the idealized efficiency. Okay, heat transfer to thermal reservoir at 200, 300, and 400. Determine whether the cycle operates irreversibly, operates reversibly, or impossible. Okay, so we know the actual cycle efficiency is 1 minus QC over QH, and we have QC over QH. But we also know the ideal because we have the temperatures of the thermal reservoirs at 3 different points. So as you can imagine, probably what's going to happen is that we will be able to excuse me. So we will be able to actually see whether these cycles are possible or not. So here, the way the solution goes is that you have calculate the thermal efficiency based on heat transfers. So eta, which is the thermal efficiency, is equal to QC over QH. That's the actual, right? So that's the actual efficiency that we have there. So that equation reflects the actual condition. Now, the theoretical maximum performance is what you would get if we use the temperatures of the thermal reservoir. So 200 minus 200 in this case, or in 500. So if we do the first case where the lower thermal reservoir is at 200, we have the case where the maximum thermal efficiency is 0.6. So the actual thermal efficiency is less than the maximum thermal efficiency, so everything is good, right? Everything is good. Irreversibly, so we have an irreversible system, right? If we have TC over TH equals 300, which is 500, I'm sorry, 300 is the low temperature reservoir. We end up getting that. The maximum thermal efficiency that you can get is 0.4, and so it happens that the actual thermal efficiency was 0.4, which means that the cycle was reversible. So not really attainable, but you can always try, right? So we have a reversible cycle. In the case of C, you have 1 minus 400 over 500. So in this case, the ideal cycle is 0.2. And so the actual cycle was 0.4, which means that the actual cycle had higher thermal efficiency than the ideal cycle, which is not good. You can't do it, right? So that's impossible. So we'll say that that's an impossible cycle right there. All right, so I'm giving you an example to do in your homework, which is largely similar to this. You just have to manipulate the equations a little bit to determine whether the cycle is real or not, or possible or impossible, based on these relations. So hopefully that's something you can do easily. Okay, so now I think I have another example here somewhere. Oh yeah, okay. So I'm going to talk a little bit about the ideal power cycle. And I'm talking a little bit about Carnot cycle. So the Carnot cycle provides a specific example of a reversible cycle that operates between two thermal reservoirs. Other examples are provided in Chapter 9. So we're going to hopefully get to Chapter 9. It seems like we're never going to get there, but we might get there. The Ericsson and Stirling cycles, some of my favorite things to do is cycle analysis. So hopefully we get there. In the Carnot cycle, the system executing the recycle under 4 internally reversible processes. So it's a completely reversible cycle. 2 adiabatic processes with 2 isothermal processes. It looks like the following. Okay, so it looks like the following: the PV diagram and the schematic. So here we go with an ideal Carnot cycle. So an ideal Carnot cycle operates according to 4 processes. And of course, here we see the classic piston cylinder configuration again. So you see, this is a pretty common thing in thermodynamics to see, to use. But here you go, PV diagram, and you have 2 constant isobars, constant temperature lines. You go from process 1 to 2, you compress adiabatically, isentropically actually. Isothermal expansion, you come down, so adiabatic compression, and it's reversible, so therefore what we call isentropic process. And then 2 to 3 is when we have expansion. So we have isothermal expansion, meaning the process is happening at the same temperature, which is difficult to achieve actually. And then you have 3 to 4, which is adiabatic expansion, and then 4 to 1 where you compress, and then you start back again at 1, which makes it a cycle. Okay, so this is, since it's an idealized cycle and it's all reversible processes, we can say that this is a reversible cycle. Okay, so here we have the PV diagram, the schematic of water executing a Carnot cycle through interconnected. So here's an idea like how one could execute a Carnot cycle. And if you do this analysis, you can see that by each of these cases, the thermal efficiency is given by 1 minus Tc over Th. That is the idealized efficiency of a power cycle. We may go through Carnot cycle a little bit more in detail as we go further, and I probably do some examples of Carnot cycle. But I'm not going to talk too much about cycles right now because I really just want to get to the concept of entropy. Carnot cycle is pretty cool. You can see that this is just one example of how one might be able to achieve a Carnot cycle in a system of steady state control volume type analyses. We have a pump, a boiler, a turbine, a condenser. This is actually like a steam power plant. So this is like a Carnot cycle, right? And the idealized efficiency is given by the same equation as the maximum efficiency. The Carnot cycle varies with temperature. So this maximum thermal efficiency or maximum thermal efficiency varies as 1 minus Tc over Th. And just kind of, I wanted to throw this slide in here because it's interesting to see that as Th is equal to Tc, then you have 0 efficiency, right? Which is possible. If you have no Th, you have 0 efficiency. As you go into intermediate temperatures, the efficiency really climbs very steeply for the Carnot cycle, from kind of point A to point B. And then from point B on, essentially you've got approaching 100%. So as Th goes to infinity, you have kind of an infinite efficiency. But typically around the temperatures that we can attain, 2000 degrees Kelvin is like pretty hot, like combustion type temperature. And you can see that you have sort of a peak out of a Carnot efficiency maximum. And so you end up reaching this idealized efficiency. Now, you can never get to this Carnot efficiency. It's sort of an idealized process, as I said. Everything that is in actual practice has an efficiency less than this for a cycle, thermodynamic cycle. So if we go now and do another quick example, so one kind of final example that we can do is to look at an ideal power cycle. So a reversible power cycle whose thermal efficiency is 40% receives some heat, 50 kilojoules, by heat transfer from a hot reservoir at 600 and rejects the energy to the cold reservoir at Tc. So let's determine the heat rejected and determine the heat rejected at in kilojoules and also the temperature of the cold reservoir. Okay, so let me bring back my notes here and we can do this example 2. So where is it here? All right, here we go. So now let's do this example here. So yeah, let's see, let's gonna get this right. So the reversible cycle and yeah, so I think I've got the right thing here. So I just want to make sure I've got my right notes here on my other part of the screen is where I'm kind of looking at my notes. So that way I can keep it all together here. Okay, so let's let's start this example. So known, we have the known as a reversible power cycle. Um, we'll say data provided for a reversible power cycle. What we need to find is the energy rejected in kilowatts, so QC, that's the energy rejected. When you say the energy input would be QH, the QC, and we need to find TC, which is the temperature, the low temperature reservoir, okay? The efficiency is given, so analysis. Oh, I'm sorry, I want to do assumptions first. Okay, so the assumptions are that, let's see, one, we have steady state cycle. Two, it's reversible cycle. Okay, and you might be able to hear my kids yelling in the background. It's their spring break this week, and they're complaining that we're making them do work. But if we don't do any work, as you probably know, if you're idle, things go a little wonky. So you may hear them screaming and complaining in the background as we're going along here. But that's just life now, right? We're all doing everything together at home. So let's see. Let's finish this example and we can be done for today. So the thermal efficiency is given. So yeah. So let's just go on here. So we have a thermal efficiency 40%. So if we make a diagram, it's probably good to make a diagram. It's always good to make a diagram, in my opinion. Okay. So let's do that. So we have a TH over here. We have a power cycle where we have some work coming out. And we have some TC over here. It's a reversible power cycle. Just choose that little arrow thing in the cycle. Okay. And then, yeah, we have some QH and some QC going on here. Okay. So this is our reversible power cycle. Our thermodynamic system is this. This is our thermodynamic system. Okay, now we'll do our analysis. It's a pretty simple analysis, actually. Essentially, since we know that the efficiency of the power cycle is equal to the work over QH, which is 1 minus QC over QH. Right? We know that I think we're given 50 kilojoules and TC. So we're given a couple things. So we can figure that out. We can figure QC out pretty easily. So QC is then C. So we know this is 0.4. Let's just figure this out. So QC over QH is equal to thermal efficiency, 1 minus thermal efficiency. 1 minus thermal efficiency, which is, since we know the thermal efficiency is 0.4, this is 0.6. So then we know that QC has to be equal to 0.6 times QH, which is 50. So it's 0.6 times 50 equals 30 kilojoules. Oh, this is 50 kilojoules. And this is 0.4, right? According to the problem right here. And then, so that's part A. We'll just say A. And then we'll just say part B is down here. So part B, essentially, we need to know that the thermal efficiency of the is also equal to, the ideal thermal efficiency is also equal to 1 over TC over TH, because we're using the Kelvin temperature scale. And so then, you know, TC over TH equal to 1 minus eta. And so that is equal to the same thing, equals 0.6, which is also the same ratio. Oh, so that's interesting, right? So then TC is 0.6 times TH. And TH is, what did we say it was? TH is 600K. 0.6 times 600 is 360 degrees Kelvin, which is the temperature of the cold reservoir. Okay, now we can always just say that we can just confirm. Let's just do a little, since we have a couple extra minutes here. So example 2 continued. We can do a check. So then we're going to check the Kelvin temperature scale by saying that QC over QH is supposed to be equal to TC over TH, right? So let's check that. QC over QH is, well, we'll just say that if we want to solve this way, we can do TC is equal to QC over QH times TH. And if we assume that we used part A to solve for QC, we'll have, let's see, QC over QH is 0.6 times 600, which is equal to 360. Okay. Right? So we have the same answer here as we had here. So QC, let's see, QC over QH, QC is 30. Right? So that's the deal, right? So we have the same thing, and we can check the reversible work is 1 minus QC over QH, and everything works out mathematically fine. Okay, so essentially the main point of today's lecture was that when you have an idealized efficiency or coefficient of performance, that you can replace the ratio TC over TH with QC over QH. Okay, so that's the main point on the Kelvin temperature scale. And you can compare the idealized process by replacing the TC over TH with the actual process if you're given the heat. Okay, hopefully that all made sense to you. And good luck with your homework. And let me know if you have any questions or comments, as usual. Okay, take care.